Hi everyone, welcome back. In a roller coaster, the initial gravitational potential energy is continually converted into kinetic energy and heat, and some of that energy is converted back to gravitational potential energy. This is, as I'm sure you know, an example of conservation of energy. So this video will review the key ideas of work, power and energy from GCSE and introduce some of the applications at A-level. We will look at the key definitions and some worked examples. So this topic is pretty straightforward, but the ideas are hugely important and are used throughout the whole A-level course. Enjoy the video. Okay, work, power and energy. So this is basically a recap of GCSE, and most students find this particular topic in mechanics pretty straightforward. However, it's really important we understand how to do the basic calculations, and also these definitions which you've probably seen before or a version of them. It's really important that you understand the significance of them. So we've got these formula here which we'll practice in a couple of minutes. A few key definitions. Energy is a scalar, right? It cannot be negative, very important. Work done is basically F times D, as we have here. And if you write that as a definition, that won't get a mark. It's the product of the force and the distance, so F times D, moved in the direction of the force. Now, you might remember that from GCSE, but that's a really important point for later on in this topic, as we will see. So basically, if a force moves a distance, then energy is transferred. That means it's converted from one form to another. Really important. Definition of the joule you've probably seen before. So that's related to W equals F times D. If I have 1 Newton and it moves a distance of 1 meter, then the energy transferred is 1 joule. So really useful. 1 joule is 1 Newton times 1 meter, and actually 1 joule is 1 Newton meter. Those units are interchangeable. Energy is a bit of a slippery concept because it's linked to work, and we've kind of defined work some other way here. The stored ability to do work is the definition of energy. I'm sure you all remember this one from GCSE, students always do. Conservation of energy, that's very important. And then power is work done divided by time. So we've got to be careful, the units are W watts, but here this is W for work done, so possible confusion there. So energy per unit time, or the rate of transfer of energy. Okay, so that's all our basic GCSE concepts. So we're just going to rattle through some basic calculations. These should all be really easy, or pretty easy, but if you cannot answer these, then you're really going to struggle at A-level. So if you have a basic question 1, 15 newtons, 4 meters, that's really easy. We've got 60 joules. So we've got a force of 15 newtons, moves a distance of 4 meters, the energy transferred is 60 joules, nice and easy. The next two, again, GCSE standards, GPE, mgh, mass times g times height, nice easy calculation. Remember we're using 9.81, not 10, as you might have done at GCSE. And we get our 2, 3 or 4 sig figs would be fine, and we've got joules. Half mv squared, again, a standard at GCSE. Just make sure we're only squaring the velocity. So some students square everything, it's just the velocity squared, times by 50, and then divided by 2 or times 0.5, and we get 900 joules. Also at GCSE, you might have done this one. A little bit more tricky, so there's no cheat triangle rule here for rearranging. You've got to be confident with rearranging formula. So we need to make V the subject, so we take 2 from the bottom to the top, divide by m and square root. So this basic rearranging is really important, and then we can stick the numbers in. And we've also got to be careful of prefixes. We've got mega 10 to the 6 here, got to include that, and we get 22.4, sounds about right. Question 5, we've got power is work done divided by time. Again, straightforward. Watch out for the kilojoules, that's 10 to the 3. And watch out for the units of time. We need to be in seconds. So if we have 2 minutes, it's going to be 2 times 60. And we get 500 watts. So again, be careful. In this context, that's the symbol for the unit of power, watt, whereas elsewhere it might be the quantity work done. Efficiency, we seem to, we missed one out. Question 6, yeah. Question 6 is conservation of energy. So this is getting a bit more tricky. You might have got one like this at GCSE, but this would be quite a tricky one. There are two ways we could do this. We could use a Suvat formula for this, which is absolutely fine. But in the context of energy, then we've got to consider conservation of energy. So we have MGH, that's our potential energy, and all of that is converted into kinetic energy just before impact. So even at A level, we would normally ignore friction and energy losses due to air resistance, but you might get a question where you have to take that into account. But in this one, we can just assume that MGH is equal to half mv squared. Now, you might be looking at this and thinking, well, what about the mass? We don't know the mass, but we don't need the mass because we have the m here and we've got the m here as well. So the mass cancels. So the velocity, the final velocity is independent of the mass. Counterintuitive idea. So the mass cancels and we can make v the subject. That's equal to root 2gh, brackets there possibly, and we can put the numbers in and we get 14 meters per second. So this is very similar to as if we use the Suvat formula, v squared equals u squared plus 2as, we would get the same answer. So it's the same physics in a slightly different format. Efficiency should be straightforward. Just be careful when you're writing this. If you say the energy out divided by the energy in, well, that's actually 100%. We've got to define the useful energy. That's really important. So we need to think about, well, what is this this device trying to do? Well, we'll try if it's a car, then the useful energy is the kinetic energy, 35 kilojoules. And obviously this is simplistic because part of this might be electrical energy for the lights or something else. But in simple terms, it's going to be 35 kilo or 35 divided by 120. Well, I've just ignored the kilo here because it's the same on top and bottom. And then we could write it as 0.29. If we want it as a percentage, we have to multiply by 100. The final thing, again, you might have seen from GCSE, is this formula here, P is equal to F times V. Now, some specifications at A level include this in the formula booklet and some don't, but it's a really, really useful one. Power, if we're moving at constant velocity, power is equal to the force, the driving force, or the resistive force, which will be equal, multiplied by that constant velocity. So if we know that, we can just put the numbers in, but we can actually derive it from P equals W over T. So W, as we know, is equal to force times distance, and then we have distance over time. Distance over time is speed, or in this case, velocity, and we get F times V. Okay, so this is all the basic calculations from GCSE. You might get questions this simple at A level, but they're probably going to be more difficult, but we have to know these basic ideas. Okay, so two more things to consider. Again, this one you might have done at GCSE. It's a really, really useful, very important idea. So this is a work done and braking distance. So normally we'd be talking about a car braking, but it could be any other object slowing down. So in this case, we need to think about, well, what's actually going on? How do the brakes work in a car? Now, there's different types of brakes, but most modern cars have disc brakes. So on the axle, just behind the wheel, you have these discs which are rotating, and you have these calipers or pads which are compressed by the brake fluid when you push the brakes, and they basically squeeze the disc and you create a huge amount of friction. So if you're doing a lot of braking at high speed or going down a mountain road, then the discs get hot. They may even get red hot. So we're converting kinetic energy into friction and a little bit of sound. So this is all to do with W equals F times D, and we need to go back to our definition. We said that work done is the energy transferred. Well, that's what we have here, kinetic energy into heat energy when a force moves a distance. Right, so we're applying a braking force, which we assume is constant, and we're slowing down. This is our distance. So this is only for if we apply the brakes until we come to a complete stop, or well, not only, but in this context, that's what we're going to look at. So this is the key thing here. This means that the work done is equal to the original kinetic energy. That's the key idea here. Once we've got our heads around that, then the next part of the calculation is pretty easy. So all the kinetic energy of the car is converted into heat. So that is equal to the work done by the brakes. Right, so this is your typical example. We've got a car of mass 1.5 tons, metric tons, moving at 15 meters per second. The driver brakes until coming to a halt. We assume a constant force of 2,300. Calculate the braking distance of the car. Now, you might have done a question like this at GCSE. If you're not sure what to do, the first thing is, well, what can we calculate? We've got the mass and we've got the velocity. Well, we can find the kinetic energy, half mv squared. It's this really big number here. So remember, the joule is actually a very small unit of energy. So very often we're talking about big numbers in joules. And this is not ideal for writing the way I've written this. That's 5 sig figs. We probably only write 2, 3 or 4 sig figs, but it doesn't really matter for this calculation. Okay, the next part is absolutely essential. We've found the kinetic energy. We need to assume that the kinetic energy is equal to the work done. That's just a statement. So there's no calculation there. But once we've made that realization, then the next part is quite easy, because we know that work done is force times distance. So we know the work, we've just calculated that, the same as the kinetic energy. We're given the force, we assume that's constant, 2,300. So I can just rearrange W equals F times D to make D the subject, D is equal to W over F, and that becomes a straightforward calculation. It sounds about right. That's relatively fast. It's quite a heavy car, 73 meters. Okay, well, that doesn't necessarily mean the emergency braking distance, but with this applied force, then this is how long it will take. So we can use this approach for not just braking cars, but for any object which is slowing down and converting its kinetic energy into heat energy. So very, very important you practice that. And the final thing we're considering in this video is components of forces. So again, we need to go back to our definition of work done. We said that's the product of force and distance the product of distance and force when the force is moving in the same direction as the distance. And we always assume that at GCSE. But what about if we have a more complex situation where the force is not moving in the direction of the distance? And typically this might be an object being dragged by a rope, and rather than the rope being horizontal, the rope is at an angle. So the distance moved by the object is horizontal, but the force is at an angle theta. Now there is a formula here. It's usually FD cos theta or Fx cos theta. So it's the force multiplied by the distance multiplied by the cos of the angle. And all we're doing here basically is working out the component of the force in the direction of the distance. So the adjacent component, the horizontal component, is F cos theta, and that gives us the cos theta and the F multiplied by D. So it's the same physics, it's basically F times D, but now we're talking about the component of force moved in the direction of the distance. So this is where those definitions are really important. They're not just the easy marks for the 1 or 2 mark questions in the exam. They're the fundamental principles that you must understand in order to answer the more difficult questions. So the questions tend to be fairly straightforward. So here we've got a nice historical industrial example. So we've got a barge and a canal, lots of physics and interesting stuff about the development of science and the Industrial Revolution to consider there. But we've got a pack of horses here, a really long rope, and this is what the towpath, you've probably heard of towpath, and you may not have considered that's what they did. You had a load of horses towing a barge, and this was the arteries of the Industrial Revolution around certainly Britain and some other countries, but certainly Britain. Anyway, we have the barge is moving forwards by 200 meters. That is our distance. The force is 400 newtons in my made-up example, and we need the component acting forwards. So that's going to be 400 multiplied by cos 30. So that's this forward component, and then we multiply by 200, and that will give us our work done. Right, so hopefully most of this video is just a recap of ideas that you knew from GCSE. And what we tend to find is that the context and the complexity and the other things to consider are more difficult. So it's all these ideas from GCSE, but in more difficult scenarios. But very, very important, work, power and energy are used throughout the 2-year A-level physics course. So you've got to be really, really confident with these basic ideas to make sure you can answer the more difficult questions. Okay, so what's next? The next in this series, in the mechanics series, there should be a video on moments, so you might want to watch that one. If you want more structured lessons and quizzes and exam tips and loads more resources, then go to payhip.com, grade A Physics. I hope that was useful. See you in the next video.